In the next section of chapter 14, we'll look at some reactions of acids and bases and then the idea of acid-base titration. We already talked a little bit about neutralization reactions. So when we mix an acid and a base, we get the proton from the acid combining with the hydroxide from the base, and it forms water and some kind of a salt, generally, from the unused anion and cations from the acid and the base. So the ionic compound, the salt that's formed, remains dissolved in solution. So the salt contains the cation and anion that come together, but if we look at the net ionic equation, the salt that's formed involves spectator ions. Nothing's happening with those. The net ionic equation ends up being this for many neutralization reactions. Now, it's dependent on some various conditions that have to occur, but you will get this reaction going on with a neutralization. You may have other things going on as well. H plus OH minus yields H2O. We looked at this briefly in a previous chapter. If we look at some particular acid-base reactions, there's some interesting things that we can note from those. For instance, if we look at the reaction of carbonate or bicarbonate compounds, so remember your polyatomic ions for carbonate and bicarbonate, when we react compounds containing those with acid, we still produce water, as we said before, but we also get carbon dioxide as a gas and the salt as well. So we get this additional product of carbon dioxide. And we have, again, looked at this type of reaction. This is known as a gas evolution reaction. So for example, if we mix sodium bicarbonate, baking soda, with hydrochloric acid, any type of acid will do. You can mix it with vinegar and get the same reaction, but here we're looking at hydrochloric acid. What we end up getting is water, carbon dioxide gas, and salt, sodium chloride, table salt. So if we were to carry out this reaction, we would end up with salt water once all the carbon dioxide bubbled out. We also said that many metals will dissolve in acid. The reaction between a metal and an acid will generally produce a gas. Now, it's not carbon dioxide in this case, it's hydrogen gas. And we also get the dissolved salt, which contains the metal ion. So for example, if we were to take a strip of magnesium metal as a solid and combine it with hydrochloric acid, the gas that would bubble off would be hydrogen gas. If you were to, very carefully insert a lit splint in there, it would burst into flames. It might even pop a little explosion there, so not recommended that you try it. And magnesium chloride as a dissolved compound. Now, there are a lot of metals that are reactive with acid. So 3 examples shown here are the reaction with magnesium, zinc, and iron. Okay, various acids that will react with those. For the magnesium and the iron here, it's shown them reacting with hydrochloric acid. With the zinc, it's reacting with sulfuric acid. And you can see that all 3 of those reactions produce hydrogen gas and some sort of a metal salt. Now, we already stated earlier that some metals are resistant to reaction with acid, for instance, gold. So the reason James Bond carried the acid in a gold pen is because most acids don't react with gold. He would spray the acid on iron bars to get it to dissolve. Well, if somebody were to put James Bond in a prison made with gold bars, his pen full of acid wouldn't do him any good in that case. Now, there are ways to determine whether or not a particular metal will dissolve in an acid, and that is talked about in chapter 16 of your book in reduction-oxidation reactions. So if you want to know more about that, I suggest you do go to chapter 16 and read through that chapter. Acids react with metal oxides. So now we're not talking pure metal, we're talking about an oxidized metal. So we know that iron oxidizes very readily to form what we call rust. So we're talking about that sort of thing, something that's been oxidized. An acid can react with that as well, and it will produce water and a dissolved salt. So for example, in the first case shown here, we react hydrochloric acid, HCl, with potassium oxide, and this will form water and potassium chloride in solution. I can take hydrobromic acid, react it with magnesium oxide, and again, notice here, my stoichiometry, I have to have two of the acids to react with one of the oxides here. So the two H's combining with the one oxygen to form H2O, and then the ions that are left, magnesium and bromine, combine to form that metal salt. Same thing up here. So two hydrogens with the one oxygen, we get an H2O, and then potassium with the chlorine, and we get our salt that we've already looked at. So those are reactions with acids. What about reactions with bases? If we look at neutralization reactions for bases, and we look at a particular example, so in this case we look at the reaction with aluminum, we can see that the most important base reactions that we get are those in which we are neutralizing an acid. So we've already looked at acid-base neutralization, forming water. But we want to look at one other kind of base reaction here. The example shown is the reaction of sodium hydroxide with aluminum metal and water. Now, why is this particular reaction important? Well, it turns out that aluminum is one of very few metals that will actually dissolve in a base. Aluminum is also easily dissolved with acid, so aluminum tends to be easy to attack and to dissolve and break down. So this is why you don't see aluminum used in areas where you need a high resistance to corrosion. So for example, if you were to make plumbing pipes out of aluminum, you wouldn't be able to use your Drano drain cleaner because that's made of sodium hydroxide, which is a strong base. And we'll talk about strong and weak acids and bases, but you wouldn't want to use that because it would dissolve your aluminum pipes. You end up getting this sodium aluminum hydroxide compound, which dissolves readily in solution, aqueous in solution, and you get hydrogen gas out of that. Okay, so for this reason, the use of aluminum pipe and aluminum joins for buildings is forbidden by most building codes, just because it doesn't have that durability if you were to use these typical cleaners that are basic. Now we want to talk about the idea of acid-base titration. Now, a titration is a way to measure something about one solution, an unknown feature of one solution, by comparing it to and reacting it with a solution that has known characteristics. And in this case, we want to measure an acid against a base, or vice versa. So when we do this, we have to go back to that idea of solution stoichiometry. We've talked about solution stoichiometry already. This is an important feature to note. It's an important concept to understand when we talk about an acid-base titration. Okay, so what we're going to do is take a substance in solution that has a known concentration, and we're going to react it with something else that has an unknown concentration. In the reaction shown here, we're going to take hydrochloric acid and react it with sodium hydroxide. This will form water and aqueous sodium chloride. And we want to be able to, maybe if we know something about the sodium hydroxide, use that to calculate something we don't know about the hydrochloric acid, or vice versa. All right, so looking at that, thinking about that one as the example, hydrochloric acid and sodium hydroxide. We're going to represent an HCl solution by the diagram shown here, where, again, the chloride ions are going to be spectators. So we're not going to show those. We are going to show, and the other thing we're not going to show is the water molecules. It's in aqueous solution. The water molecules are there as a carrier. The only thing we are really interested in this reaction is the H+, the proton. So we're going to show just those floating around in solution. Now, in the base solution, that contains the hydroxide, same thing. The sodium ion is a spectator. The water molecule is just a carrier, so we're not going to show those. We're not going to show those, just like we didn't show these and we didn't show these. We're going to show just the molecules or the ions that are part of the net reaction. We're going to get rid of all the spectators here. So, keeping that in mind, here's our initial setup right here in the first drawing. So if we look down in the flask, we can see that we have protons in solution, and then we look up here and we've set up a burette, and in the burette we have sodium hydroxide. So there's our hydroxide compound. Okay? And what we're going to do is use that burette to then add hydroxide to the hydrogen ions, to the protons. And I'm going to do that slowly until something happens to trigger a measurement of some kind. At some point I need something that alerts me to the fact that, okay, so I'm dropping a hydroxide in here, and every time I drop in a hydroxide, okay, so this thing comes down, and it's going to pick up one of these protons and bind it together and form a water molecule. And then I add another one in here, and it binds to one, it forms another water molecule, and here's another one that can react there, here's another one that can react there, and then the next one comes out of here, and it's going to react right there. At that point, okay, notice here's my cutoff, so those, I stop right there. I don't add those to solution, because at this point there are no protons left in solution. There's no extra hydroxide. I'm looking for something to happen. Now notice this drawing. Here they've shown it as a clear solution, and here it's shown as pink, and we'll talk about what that is. But the idea is that the number of moles of the reactants that are in here, and pretend like we didn't know that there were 5 in there, okay? But the number that are in here are going to be stoichiometrically related to the number that I add until something happens. So now I can say, okay, well, how many of these did I have to add to make something happen? I had to add 1, 2, 3, 4, 5. Okay, and they actually should have drawn one more in here. So I used up 5 of those, and I know that it's a 1-to-1 reaction, so that tells me there had to have been 5 of these protons in the solution to start with. Okay, so hydroxide is added, reacts with and neutralizes the protons, and we get water molecules. What we're looking for is something known as the equivalence point. Equivalence, we're looking for the point at which it is equal, at which the number of moles of hydroxide that I've added equal the number of moles of hydronium ions or protons that I originally had in solution. That is the point at which I complete my titration. I don't add any more hydroxide because I want to make a measurement at that point. Now, how do I know I have reached the equivalence point? I have to have something to signal that. As I said, one of the ways we can do it is by using a chemical indicator. A chemical indicator is some sort of a dye whose color is dependent upon the pH or the acidity of the solution. So in the case of the hydrochloric acid and the sodium hydroxide, we would probably be using an indicator known as phenolphthalein. And phenolphthalein is a compound which will be colorless in an acid solution and will take on a reddish or pinkish color when it is basic. So what I'm actually doing when I titrate is reaching what is known as the end point. I want the point at which I have a very, very slight excess, just one extra hydroxide in there to kick it just basic enough to make that indicator change color. Now we're talking about equivalence point here, and you'll find out as you get more into analytical chemistry that there's a difference between the end point and the equivalence point. Usually by the time you see an end point, you've actually gone a little bit past the equivalence point, and there's usually a little back calculation that you have to do to account for that. But there are other ways that you can measure an equivalence point and stop at an actual equivalence point. And if you'll remember, you did a lab in which you were trying to determine an unknown acid. So we had an acid that we knew its concentration, but we didn't know its identity. And we were looking for the number of equivalence points that we had in the titration of that acid. Well, this is what we're talking about. The equivalence point is the point at which all of a particular proton got neutralized. So for most laboratory titrations, the concentration of one of the solutions is unknown and the other is known very precisely. So if I very carefully measure volumes of solutions, I can compare the volume and the molarity of what I know to find number of moles. I know the stoichiometry, so I can go from moles of what I know to moles of what I don't know, and then I can take the moles of what I don't know and convert that as needed. So I can calculate, if I need to, a volume or an amount or a concentration, moles per liter. So for the titration that we mentioned earlier with sodium hydroxide and hydrochloric acid, when we have reached stoichiometric proportions, that is when we have 1 mole of base for every 1 mole of acid, the indicator that I mentioned, okay, phenolphthalein, and you can see it's a pretty funny spelling here, but it will turn to pink, okay? And we want a very faint pink, and this actually is almost too bright of a pink. But you definitely want to stop when you have any hint of pink which persists in solution. So you can see here it was still acidic, still colorless. Here they've added a drop and you're starting to see this buildup of the base here. So all of the acid has been neutralized at that point. Now probably for this one, if you were to pick up this flask and swirl that in, the pink color would disappear. What you want to be able to do is take that and swirl it up, and the pink color then spreads throughout the solution and creates a homogeneous color all the way through, one that persists for an amount of time. Now, what would the calculations look like for something like that? Here's a theoretical situation. We took 10 milliliters of hydrochloric acid solution that we did not know the concentration of. So we want to know, what is the concentration of this unknown solution? We take a sodium hydroxide solution that we know the molarity of, 0.100 molar, and we start adding that to the hydrochloric acid solution that has a little bit of indicator in it, and we add the sodium hydroxide until the hydrochloric acid solution just turns pink. We very carefully measure the volume on the burette of the amount of sodium hydroxide we added, and we discover that it requires 12.54 milliliters in order to reach that equivalence point. That is all the information that I need. If I have the volume of my unknown, the volume and the molarity of my known, then I can calculate the concentration of that hydrochloric acid solution. Now, what you have to be careful about, looking at this, it looks like, oh, I've got 2 volumes and I have a molarity. I'm going to use a dilution calculation. M1V1 equals M2V2. While it just so happens in this case that you could use that formula and it would give you the correct answer, the concept behind doing that is completely incorrect. So be sure that you do not use the dilution calculation for this sort of problem. If you do, even though the answer you get would be correct, it would be counted as wrong because you're demonstrating an incorrect concept here. What you would need to do, okay, if you look at what you're given, here's the volume of the unknown, and I've got a volume and a molarity for the known. What I'm trying to find is the concentration or molarity of that first solution, the hydrochloric acid. So I need to know in my stoichiometry first, what is my balanced chemical reaction? So 1 hydrochloric acid reacts with 1 sodium hydroxide to form 1 water and 1 sodium chloride in solution. It's all 1 to 1. So it makes it a little bit easier, but we're still going to show that stoichiometric relationship. We're still going to use that 1 to 1. So if we start out with what we know the most about, that is the sodium hydroxide. Okay, we know experimentally how much sodium hydroxide it took to complete the titration, so that's my starting point. How many milliliters of sodium hydroxide did I use? Okay. Now, I need to convert that to liters because I have molarity. I want to use molarity. Molarity is moles per liter. Okay, so I convert right here from milliliters to liters. When I know the volume of sodium hydroxide in liters, now I can take the molarity that I have right here, 0.100 moles for every 1 liter, And I can multiply that by the volume. Liters cancel out, and that leaves me with how many moles of sodium hydroxide it took. Now remember, for every one I drop in, it's reacting with one of those hydrochloric acids. So now I use my stoichiometry. Okay, I'm just going to abbreviate it. That's an O. Stoichiometry. And I can convert moles of hydroxide to moles of hydrochloric acid. Now, that tells me how much hydrochloric acid I had, number of moles. But I was asked for the molarity, which is the ratio of the number of moles per liter of solution. So what I then have to do is take whatever answer I get here and plug it in down here. I take that number of moles of hydrochloric acid and I take the volume that I had to begin with, the 10 milliliters that I had, calculate moles per liter, divide it out, and then I'll get the molarity. All right, so if we look at it with the numbers put in, we can see how that runs. There's two parts. The first thing I have to do is just start with the volume of sodium hydroxide, convert it to liters. Okay, so milliliters cancel out, leaves me with liters. Then I convert liters of sodium hydroxide to moles, so liters cancel out. And then I convert sodium hydroxide, number of moles, to hydrochloric acid. So step one, I have to find how many moles of hydrochloric acid were in that solution. Step number two, I take that number down here and then divide it by the initial volume that I was given, the 10 milliliters. Now keep in mind, molarity is moles per liter, so I have to convert milliliters to liters here. And then I end up with the concentration of the acid that I had to start with. Now I know that it's a 0.125 molar solution. That is a look at some reactions with acids and bases and how to carry out a titration. In the last part of this chapter, we want to define what is meant by a strong acid or base versus a weak acid or base. And strong and weak acids and bases is not related to concentration, so we'll look at what that means. We will talk about the property of water, that it is amphoteric, it's an acid and base in one. We'll look at the concept of pH and briefly at pOH, and then we will touch on how pH is important to these solutions to create what's known as a buffer.